Well, thank you, everyone. Hi, everyone, and thanks to the organizers for inviting me to speak with you today about big data analysis and geoscience. My name is Karianne Bergen, and I'm an assistant professor of data science and earth, environmental, and planetary sciences at Brown. So the main thing that I hope that you'll all take away from today's talk is that new tools for big data analysis are playing an important role in modern geoscience research. Scientists are increasingly able to take advantages of advances that are happening in computing and algorithm research to extract new knowledge and scientific insights from data sets that are larger and more complex than those that could be analyzed using more traditional methods. Big data analysis expands our capabilities in terms of the scale of the data analysis that we can perform and the kinds of data sets that we can work with. Big data analysis is also helping us create new efficiencies by automating data processing and analysis, freeing up scientists' time to do more interesting work, and help improving the accuracy of predictions and automated analysis. So why do we hear so much about big data all of a sudden? Scientists have always worked with data, but over the last, say, 5 to 10 years, there's been a lot more discussion of big data, machine learning, and these similar sorts of tools. And this is really due to 3 advances that are all sort of happening all at once that are driving innovation and progress in big data geoscience. So the first is the availability of increasingly large scientific data sets. Another is advances in computing technology. And the third are new algorithms and analysis techniques. And this is going to be the main focus of the talk, although I'll touch on the other 2. So I do want to say a word about big data sets in geosciences. These massive data sets that we're increasingly seeing in the geosciences are a challenge for scientists, but they also represent a new opportunity to gain scientific insights, to really get new insights from those data sets. But we have to have the right tools to pull out the relevant signals and patterns from our big data sets. And so these large data sets can be large in a number of different ways, and we have a number of different types of data sets we're dealing with in geoscience. So a lot of my examples are from seismology, because that's where I'm coming from. So one is large data sets in terms of the duration that we've been collecting data. So seismometers, many of them have been collecting data for years, often decades. So we have these very long time duration continuous data sets. We may have data sets that are large in terms of the number of instruments. You could have dense sensor arrays that may have thousands of sensors. But there's other kinds of data sets that we have too. We may have high resolution remote sensing data sets, which can grow large very quickly. And all of these data sets, when we need to process them, we're often processing sort of raw data that's been collected from sensors. We can also think of another type of data, which is that we need to analyze, which is post-processing the outputs of computer simulations. So we can think of actually computer simulations as generating data that we need to, say, mine to find interesting patterns or create emulators to be able to run them faster. So we can think of these large-scale simulations as a source of data, as well as sensors, experiments, and simulations. I think that's kind of interesting. And then there's also data that's increasingly coming at high volume, but low quality data. Things like crowdsourcing is generating large data sets as well. So we have a lot of different sources of data in geosciences. We're getting more and more data every year, and the rate at which we're seeing data, that we're collecting data is accelerating. So just to put some numbers to this, this is a plot of the IRIS data archive, which stores seismic data. And so you can see it's growing very rapidly, the amount of data that's in the archive. And right now it contains almost 1 petabyte of seismic waveform data. Distributed acoustic sensing is a new way of collecting seismic data. And these experiments can generate hundreds of terabytes of data, like in this Sacramento DAS experiment shown here. And then there's also high resolution exploration surveys that are often done in industry that can generate petabytes of data. So these are the kinds of large data sets we might see in seismology, and we also see in other disciplines within the geosciences as well. All right, so what makes something big data? You could say, well, if you have petabytes of data, that's big. But the way I think of big data is if your data set is too large for you to just ignore, then how big it is, then that means it's big data. So if you can't ignore the scale or the complexity of your analysis, then you are working with big data. And so there's several characteristics that make analyzing big data more difficult than doing standard data analysis. One is that you may have a large volume of data. You've accumulated a huge amount of data, and now you need to analyze it. And so for this, scalability is important. You could have gigabytes, terabytes or petabytes of data coming in. And so you need to be able to analyze that data to extract useful signals. So your algorithms will need to scale. Another challenge is the velocity of your data. You may have data coming in that needs to be analyzed in real time or near real time. This means that your analysis has to be fully automated. You can't stop and configure it when you have data that needs to be analyzed very, very quickly. And this is often relevant when you're doing hazard assessment, when you're doing monitoring for hazards, or many other geoscience applications. Another challenge could be the variety of the data. You may have data from multiple sources. For instance, you may have data from GPS and also seismometers that you want to analyze jointly. And so that even if your data sets aren't large in terms of, say, the volume of the data, you may have complex data sets if you have a number of different types of data coming in that need to be jointly analyzed. And that sort of falls under big data as well. And finally, it was something that's often referred to as veracity, just to keep up the theme with the V's, which is sort of the data quality. Like you have data that's coming recorded in noisy environments, you could have instrument error, and you need to do a lot of data cleaning, quality control, denoising. That makes analyzing the data challenging. So that also falls under big data. So those are the challenges of big data. There's a number of different strategies that we can use to analyze big data. So one is to use efficient algorithms. And I'll give an example of this next. But efficient algorithms are algorithms that scale well with the increase in data volume. So we want algorithms that will scale linearly, meaning or subquadratically. Linear algorithms, if you double the amount of data you're analyzing, the computational runtime should also double. Subquadratically means that if you double the amount of data you're analyzing, then the computational runtime should not grow more than a factor of 4. So it should say less than a factor of 4. So those are the kind of algorithms we want. We don't want the amount of compute it takes to analyze our data to grow, too much faster than the size of our data set in order to keep things efficient. So there's a lot of research on efficient algorithms, and that all falls under sort of big data. There's also a increasingly used strategy is to use machine learning, and specifically machine learning techniques that can be applied to large scale data like deep learning methods, which I'll talk about later in the talk. There's also some other approaches you can take. If you have a specific task and you know a lot about the properties of your data set, you can design custom algorithms that take advantage of the structure of your data and problem. That takes a lot more skill, and it can only be used for sort of more limited cases. If you have big data, another thing you can do is try to make your data smaller. You can try to identify which data are not very useful and reduce the amount of data. You could try to compress your data and so on. We're not going to talk about these last two as much, but all of these strategies are usually combined with our second advances in computing technology like parallel distributed computing and cloud computing that allow us to take these algorithms and run them more efficiently, more quickly, and scale them up to very large data sets. So I want to give an example of an efficient algorithm, and then I'll move on to machine learning. All right. So today I'm going to give you some examples, and these are going to be focused on a particular topic. So this is looking at using these new big data algorithms for waveform classification for detecting small earthquakes and identifying seismic phases. And so just briefly, the reason why detecting small earthquakes is important for the sciences is that these provide observational constraints on earthquake processes and stress transfer processes, things like earthquake nucleation or earthquake triggering, that are useful to help understand the physics of earthquakes, basically. So we want to be able to detect these little earthquakes. And this is a challenging problem. These events are low signal to noise. They occur as part of complex sequences. The data can be very messy. There's a lot of sensor noise. There can be quality control issues. And these are data sets grow very large in terms of the time duration or possibly in terms of number of instruments. So you do need scalable methods in order to analyze these data. So one of the approaches that we took, this was a project I worked on as part of a team at Stanford with the team members, which you can see below, which was using an efficient algorithm to try to detect more small earthquakes. So in this case, we used an efficient algorithm that was used also for efficient audio recognition. So it's not an algorithm we came up with. We adapted it from audio recognition to seismology. So it's kind of transferring this knowledge between different fields. And then the idea with the algorithm was to try to discover new event waveforms, even in the case where we didn't have any examples of what a waveform looked like in a particular area or recorded at a particular station. We were able to detect generally 1 to 2 orders of magnitude more earthquakes than were in the catalog. And we were able to do this in a computationally efficient way. So compared to a more naive sort of algorithm, which I'll describe on the next slide, we were able to process 500 times as much data with a substantially reduced runtime. So this was a new capability that we didn't have before, the ability to process 10 years of data and search for small earthquakes, as opposed to previous methods that could only be applied to small data sets. All right, so the approach that we were taking to detect earthquakes without having prior knowledge of what the waveforms look like was to use a data mining approach to look for similar earthquake signals in large data sets. So this is an example of data recorded at the Calaveras Fault in Northern California. And you can see there's 5 waveforms that are recorded over a series of years and look almost identical. So the idea was to use the fact that we know earthquake waveforms can repeat like this, search for repeating signals, and use that to find new previously undiscovered earthquakes. If we want to search for repeating signals in sort of a naive way, to just search through the data and do kind of all-to-all comparison, looking for repeats, this is an extremely slow algorithm. It can only be applied to very small data sets, like maybe a week of data. But if we use an efficient algorithm, a fast approximate search for similar waveforms, then we can actually scale this up to decades, to up to a decade of data. So I'm not going to go into all the details of how it works. I'm happy to discuss offline more of the details or refer you to our papers. But the basic idea of how we speed up this search is to take advantage of the idea that searching a well-organized database is going to be faster than sort of looking through a disorganized database. So you can think of it as searching a filing cabinet versus a giant stack of papers that you've just thrown on your office floor and trying to find what you're looking for. So we use an efficient algorithm that clusters similar waveforms together for quick retrieval and allows us to quickly find which of the waveforms are similar to each other. Now, this does have the potential of sacrificing a little bit of accuracy. There is a small chance, in practice it doesn't really happen, but there's a small chance you'll occasionally miss an event, but you get a substantially reduced runtime and a capability to scale this up to years of data, which we wouldn't have otherwise. So it uses this sort of trade-off that's common with these big data algorithms. You might have to sacrifice a little bit to get a huge speed up. So I'm happy to talk more offline about this particular approach if anyone's interested. But I also wanted to have time to talk a little bit about a really popular method for dealing with big data sets in geosciences, which is to use machine learning, and especially these methods called deep learning algorithms, which scale up to large data sets very well. So for those of you who aren't familiar with machine learning takes a particular approach to analyzing data, which is to build algorithms that are learning the way that people do from experience. For a computer, experience means data. So these are algorithms that learn by looking at examples from data. So machine learning is a set of data analysis tools that automatically build models and recognize complex patterns using the data itself. Machine learning draws heavily on tools from applied statistics. So methods like linear regression, logistic regression, and principal component analysis are examples of sort of simple machine learning algorithms. These are things that fall under the umbrella of machine learning. And we can see what I can use it to illustrate what I mean by, say, learning a model automatically from data. Probably most scientists have fit a linear regression model before. So if you have X and Y's that you want to sort of model this, the relationship between X and Y, in this case, we'll fit a linear model, which has a slope and an intercept. And we use the data to determine what those slope and intercept values are, rather than having an expert pick them. We use a least squares approach to fit what those are using the data itself. So that's kind of the idea with machine learning, is you're using the data to fit some parameters of a model and using it to make new predictions. So there's a number of different machine learning algorithms. It's a really broad class of tools, but many machine learning algorithms that are very powerful are what are called supervised machine learning algorithms. So these are algorithms that learn a specific pattern by looking at specific examples of that particular pattern. You can also have what's called unsupervised machine learning, and that's more trying to discover structure in a data set when you don't have examples of a specific pattern you're looking for, and you're more interested in just finding certain kinds of structure. All right. So what makes machine learning such a useful tool for big data? Deep learning algorithms in particular are becoming really common. And because these algorithms, they're really data hungry. So they're really useful in big data contexts. Deep learning models have a large number of trainable parameters. And the more data you feed them, the better the model tends to perform in practice. And so a lot of the research that's been going on in the machine learning communities or the data science community has focused on innovation in computing and algorithms to scale up the training of these models so that you can actually feed it a large data set and be able to efficiently train the algorithm. So there's the tools that are available for us to feed these data-hungry machine learning methods are big data sets and learn a complex model. Machine learning is also useful in geosciences because machine learning can be used for a wide range of tasks and data sets that involve high volume data. So in this diagram, we have on the left a number of task-specific algorithms used in seismology. But what we notice here is you need different algorithms depending on your data density, which means like how close are your measurements together, either in space or time, or our data knowledge, like how much prior knowledge do you have about the data set that you're processing? And so that will affect, which kinds of algorithms you can use. Whereas we can see that machine learning can be applied across the board. We can apply it to both cases where we have dense and sparse data. We can apply it in both high and low knowledge cases, although we may use slightly different machine learning methods. But machine learning is very flexible and can be applied to a range of different data sets, which makes it a particularly useful skill to develop. So in terms of how machine learning is being used, there's kind of a set of broad areas where machine learning has been used in the sciences. So these I kind of group into discovery, modeling, and automation. And these aren't meant to be sort of mutually exclusive. These are just kind of broad umbrellas to give you a sense of how you might use machine learning in your research. So the first one is discovery. The idea is discovering patterns or insights from your data. So being able to extract new information, things like complex patterns, structure, or relationships from scientific data sets, and in particular, patterns that are difficult to find or not easily revealed using conventional analysis techniques. So that's one way machine learning is often used. It can also be used for modeling and inversion. For instance, creating a representation that will capture relationships in your data. Another one that's becoming increasingly common is learning surrogate models, or some fields call these emulators. The idea here is to combine machine learning and numerical simulations by trying to learn to reproduce a specific pattern or relationship that's embedded in a large numerical or physical model. For instance, you might want to model the relationship between one particular input parameter to a simulation and some specific quantitative output, so that you can understand the relationship between the input and output parameter without having to run the entire model over and over again, because those models may be expensive. So this is something that's, especially in climate science, is becoming increasingly popular, but also in solid Earth as well. And sort of the most common use of machine learning right now is automated prediction and analysis. So this is using machine learning to perform a complex or repetitive task that would be challenging, tedious, or infeasible for an analyst or grad student to perform, and would be difficult to write out as an explicit set of commands. So instead of trying to write out an explicit algorithm, you have the algorithm learn from data how to perform the task. And so this problem that I referred to before, identifying earthquakes, picking seismic phases, falls under this category of automated prediction and analysis. So I'll talk a little bit more about that. But one thing that I want to emphasize, again, is there's a distinction in machine learning for geosciences when we're talking about big data. And the question is, do we have big data or do we have big labeled data? If we have a high volume of data, are we in this sort of high knowledge setting where we have a lot of prior knowledge, we have a lot of examples of the pattern we're looking for, or are we in the sort of the low knowledge setting where we don't actually have a lot of examples of what we're looking for, we just have a large data set, we don't really know what's in it. So FAST, which is the method I talked about before, was designed for cases when we had a large data set, but we didn't have labels available. But more recently, there's been a lot of effort from the seismology community to put together large data sets that are labeled. And this is necessary in order to use the most powerful machine learning methods like these supervised deep neural networks. So these data sets often have hundreds of thousands or millions of earthquake waveforms. So one example of one such data set is the Stanford earthquake data set, which has over 1 million labeled waveforms. This isn't the only data set. There's also, that's a global data set. There's also regional data sets that also have a large number of labeled waveforms. So these are waveforms where you have the waveform, you know where the P and the S phases are. You might have some other information like the magnitude and so on that you can use to train a machine learning algorithm. And so now that we have these large labeled data sets, there's really been a movement towards doing supervised deep learning as an approach to this problem. So one common approach is to use a convolutional neural network. This is a relatively simple deep learning algorithm, which has multiple layers. The first set of layers are what are called convolution layers. And these learn a set of convolution kernels that, when applied to the data, extract features from the data. And then it feeds those features into a dense or fully connected output that maps the features to a prediction. So you're learning features and you're learning how to predict simultaneously. And so in this case, the prediction would be the identifying whether you have an earthquake and what phase it would be. And these convolutional neural network models achieve high accuracy. They have 98 to 90% accuracy for phase detection and classification in many cases. So these are highly accurate prediction models. Convolutional neural networks aren't the only architecture. I've listed some review papers. I'm happy to send them along to anyone who's interested. Machine learning has been using a lot of applications. There's a lot of different kinds of machine learning models, but some other ones for this particular task include FaseNet, which uses a different architecture called a UNet. There's also another widely used method called earthquake transformer, which uses what's called an attention-based model. Those are models that are commonly used to process language. So there's a lot of these different models, but what's key about these models is that they have a very large number of parameters. So the earthquake transformer has over 300,000 model parameters, and those model parameters are learned using over 1 million waveforms. So these are really large data sets. Then once the model is trained, it's very fast to make predictions. So an example, just to give you some numbers, there was a recent DAS study which used waveform data where they trained a model that could then make predictions. They took, I think it was 170 gigabytes of waveform data, and they were able to process it in 30 minutes. So once you've trained the model, for these kind of problems, the training often takes on the order of hours, maybe days if you don't have good computing. But then once you want to apply it, it's relatively fast. You can process very large data sets very quickly. If you're using GPU technology, cloud computing, parallelization, and so on. So combined with the computing advances. And the flexibility of neural networks is really an asset for us in geosciences. It gives us an opportunity to create novel architectures that are tailored to geoscience problems. So just to give you some examples of that, one of the areas that I think is interesting for future work and what I'm working on is thinking about how we can design more human interpretable prediction systems. So an example of that would be trying to solve this problem of detecting earthquakes, but using an architecture not like the FaseNet or earthquake transformer, which are difficult to understand, but to build a model where you can actually understand how it's making the decisions. That's kind of ongoing work, but using the flexibility of neural networks, there's a lot of other things that we can do. We can try to take in data from multiple sources, taking advantage of the customization of neural networks. We can take in any kind of data we want. We can try to jointly analyze data from multiple sources by learning shared representations. There's also opportunities to incorporate physics into these neural network models as well. And so there's a lot of opportunities, I think, for research in this space, which I think is going to be really exciting moving forward. So I just want to wrap up by just mentioning a few things that the geoscience community can do to advance scientific research in our field using machine learning. So one involves open science, sharing code, sharing data, and having these large community data sets that people can use to train and quickly get started with machine learning are really going to be important to compare how different algorithms perform, to get people going on research and being able to iterate on the best solutions. I think we're going to need more, more geoscience education or data science education for geoscience students so that geoscience students are prepared to use these new big data methods or to collaborate with data scientists and computer scientists on these kinds of projects. And finally, there's a lot of interesting research opportunities taking advantage of the flexibility of machine learning models to create new task-specific architectures, things like using physics, incorporating physics, building interpretable models, and so on. So there's a lot of review papers out here on these topics. If people are interested, these are a couple that I participated in writing, so I'm happy to share these with anyone who's interested. And I'm happy to wrap up, and I don't know if we have time for questions, but I'm happy to answer questions offline as well. Thank you.